So, hello friends, welcome to a lecture series on non-linear programming. So, this is the last lecture of the course which deal with search techniques. In this lecture, we will deal with two more search technique, that is Newton's method and conjugate direction method. So, what Newton method is and how it is important to solve non-linear unconstrained optimization problems, and what conjugate gradient method is, let us see. So, what is Newton method basically? Suppose you have an unconstrained optimization problem. Problem is, suppose you have to minimize a function f x where x belongs to R n. So, it is an unconstrained optimization problem. This function we have to minimize subject to x belongs to R n, where x belongs to R n. Okay. Now, in numerical analysis, we have dealt with a technique called Newton-Raphson method. This method is something similar to that method. How? Now, suppose you have a differentiable function f x equal to 0, f is from R to R. Okay. You have a differential function f from R to R such that f x equal to 0. Now, if you are interested to find the roots of this equation f x equal to 0, so we sometimes use Newton-Raphson method. What it is? It is a recursive scheme basically, in which starting from an initial guess say x1, which is given to us, or sometimes we assume x1 as an initial guess, we find xk plus 1 is equals to xk minus f xk upon f dash xk, where of course f dash xk should not equal to 0 for all xk, it is a derivative. So, this is, I am not going to the much detail of this method basically, that how this method is arrived. I am simply illustrating that this Newton methods to solve unconstrained optimization problem is comes from Newton-Raphson method. What Newton-Raphson method is? That this method is basically, suppose you have function f from R to R, okay, which such that f x equal to 0, and you are interested to find out the roots of this equation. To find out root of this equation, we use this recursion algorithm. X1 initial guess is known to you, suppose. In a similar way, suppose you want to minimize this f, okay, subject to x belongs to R n. Now, whenever we have to minimize or maximize a function, that means we have to find out a derivative of the function, put it equal to 0, all those points where derivative is equal to 0, that will give the point of maxima or minima. Basically, we are interested to find out those points where derivative is 0, because those are the stationary points where the function will assume will take maximum or minimum value. Okay. So, basically to find out the points, if this function is differentiable, to find out the point where this attains its maxima or minimum, we are basically interested to solve gradient of f x equal to 0. We are interested to solve this equation, basically we are interested to find those x where gradient of f equal to 0, because all those x where gradient of f equal to 0 gives a stationary point where f will attain maxima or minima. Okay. That means basically we have to solve this equation. Okay. Now, this is a gradient, not a derivative. Okay. So, we will use this recursion f x k plus 1 equal to f x k minus Hessian matrix of f at x k, its inverse, and gradient of f at x k. So, basically it comes from here only, here itself. Okay. Basically, instead of solving this equation, we are solving this equation. And these are system of equations basically, because it is a gradient. Okay. Now, how we obtain this result, how we obtain this expression, let us see. This comes from Taylor series approximation. Okay. Now, to find out the derivation of this expression, let us write the Taylor series quadratic approximation of f, this f, Let us try to find out Taylor series, by Taylor series the quadratic approximation of this f at xk in the neighborhood of xk. How we can write it? It is fxk plus x minus xk transpose gradient of fxk plus 1 by 2 x minus xk transpose Hessian matrix of f at xk into x minus xk. This is the quadratic approximation of this function about xk. Okay. Now we know that gradient of fx must be 0, gradient of fx must be 0 for the stationary points. So, this implies basically this is 0 because this is a fixed value. So, gradient of this will be 0 and x into this will be the gradient of fxk when we take gradient both the sides, and this will be plus x, this will be plus Hessian matrix of f at xk into x minus xk equal to 0. So, this implies Hessian matrix of f at xk x minus xk is equals to minus gradient of fxk, and this implies x minus xk. Now, we assume that the Hessian matrix at xk is invertible, then only we can take the inverse both the sides. Okay. So, we are assuming that the inverse of Hessian matrix for each xk exists. Okay. So, this is negative of Hessian matrix of xk inverse gradient of fxk, and this implies x equals to xk minus Hessian matrix of f at xk inverse gradient of fxk, and we write it xk plus 1. So, in this way we can derive this result. So, this is basically Newton's method to solve unconstrained optimization problems. Okay. So, the limitation of this method is that this method will proceed only when the Hessian matrix at xk is invertible, only then we can proceed by Newton's method, but its conversion rate is much faster and it has a descent property. Descent property means for each sk the value of f will decrease. Okay. So, its conversion rate is 2 and it has a descent property. For solving quadratic functions involving positive definite quadratic form, that is the Hessian matrix is positive definite, it will take exactly one iteration to find out the optimal solution. That is the beauty of this method, that if we have a quadratic programming problem, suppose where the Hessian matrix is positive definite, then it will take only one iteration to find out the optimal solution. Okay. Now, suppose we have this problem and we want to solve this problem, let us suppose using Newton's method. So, how can we proceed? So, problem is basically f equal to x1 square minus x1 x2 plus 3 x2 square. Okay. So, this is the problem, and the initial approximation which we can take is 1 comma 2. It is capital X1 which we can take as 1 comma 2. Okay. So, using Newton's method, first we find gradient of f. Gradient of f will be, it is 2x1 minus x2 and it is minus x2 plus 6x1. It is del f by del x1, del f by del x2. Okay. And what is Hessian matrix of f? It is 2 minus 1 minus 1 6. And is it positive definite? So, when you take it is 6 x2. Okay. It is x1, sorry. When you find gradient of fx, del f upon del x1 is this thing, del f upon del x2 is x1 plus 6 x2. Okay, from 6 x2 from here. Now, when you find Hessian matrix of f, it is 2, it is minus 1 and 6. Okay. Now, this Hessian matrix when you compute d1 it is 2 which is greater than 0, and d2 when you compute it is 12 minus 1 which is 11 again greater than 0. So, the Hessian matrix is positive definite. Okay. So, Hessian matrix is positive definite and it is free from x1 and x2. It is a fixed matrix. So, what is its inverse? Is it invertible? Yes, it is invertible because it is a positive definite matrix and every positive definite matrix is invertible. Okay, it is invertible. So, what is the inverse of this matrix? Inverse will be 6, 2, 1, 1 and determinant is 11 divided by 11. So, this will be the inverse of this matrix. So, we will use this recursive algorithm to solve this problem. Okay. Take the transpose of this. Okay, yeah, it's okay. You need a column vector here, so it is okay. So, when you take x2, it is x1 minus Hessian matrix of f at x1, its inverse gradient of f at x1. Now, it is equals to x1 is the first initial guesses 1 and 2 minus. Okay. Now, inverse of the Hessian matrix is 1 upon 11, it is 6, 1, 1, 2 and gradient of f at x1 is when you take x1, x1 is 1 and 2, it is 1 and 2 that is 0. When you take 1 and 2 here, it is 11. So, gradient of f at x1 is 0 comma 11 and it is 1 2 minus, it is 1 by 11. When you take this row, this column, it is 11, this row, this column, it is 22 and it is nothing but 1 2 minus 1 2 which is 0 comma 0. So, x2 is 0 0 and 0. Now, when you compute for x3 here, when you compute for x3, what is gradient of f at x2? When you put 0 comma 0, it is 0 0 and of course, when it is 0 0, 0 0 into this will be 0. So, xk plus 1 will be xk, that is x3 will be x2. So, that means in the next iteration coincide with the previous iteration, that means the optimal solution is 0 and 0. So, x1 equal to 0 and x2 equal to 0 is the optimal solution. Okay. So, it exactly takes one iteration to solve this positive definite quadratic programming problem. Okay. So, in this way, applying Newton's method, we can solve an unconstrained optimization problems. Now, the next method is conjugate gradient method. So, what this method is, let us see. So, before setting the method, we have some terms, let us define those terms. First is conjugate directions. So, let H be a n cross n positive definite matrix. Okay. The two vectors S1 and S2 belongs to Rn are said to be conjugate with respect to H if S1 transpose H S2 equal to 0. If this equation hold, that is S1 transpose H S2 equal to 0, where H is a positive definite matrix, then the vectors S1 and S2 are called conjugate vectors with respect to the matrix H or conjugate directions. Now, if H equal to identity matrix, then S1 and S2 are orthogonal vectors. We already know that if it is an identity matrix, then this is S1 transpose S2 equal to 0, that means vectors are orthogonal vectors. Now, we have a theorem, let S1 S2 up to Sn be a set of n non-zero conjugate vectors with respect to a given positive definite matrix H. Okay. Then the set of vectors S1 S2 up to Sn are linearly independent. So, if we have a set of vectors are S1 S2 up to Sn. These are set of vectors which are conjugate vectors with respect to a given positive definite matrix H. Okay. Then we have to show that these vectors are linearly independent. So, how to show? Take a linear combination of these vectors, put it equal to 0, and if anyhow we prove that all alphas are 0, this means vectors are linearly independent. Okay. So, if it implies that all alphas are 0, that means vectors are linearly independent. Now, suppose you multiply both sides. So, this equation is given to you and you have to prove that all alphas are 0. So, you multiply both sides by, suppose S1 transpose H. If you multiply both sides by this factor, so what we will obtain? We obtain this into alpha 1 S1 plus alpha 2 S2 and so on alpha n Sn equal to 0. This implies since alpha 1 is a scalar, so it can be taken out alpha 1, it is S1 transpose HS1, alpha 2 is a scalar, can be taken out S1 transpose HS2 and so on alpha n S1 transpose HSN. Now, since S1, S2 up to Sn are conjugate vectors or conjugate directions with respect to a fixed positive definite matrix H. So, this means Si conjugate H Sj equal to 0 if I not equal to j. Okay. This means this is 0, then this is 0, all other values are 0, only this value will be non-zero. Okay. And since H is a positive definite matrix, so S1 transpose HS1 will be strictly greater than 0. So, S1 transpose HS1 will be strictly greater than 0. Okay. So, it is non-zero value. So, this implies alpha 1 equal to 0. So, similarly, if you multiply both sides by S2 transpose H, then it will give alpha 2 equal to 0, and similarly if you multiply both sides by Sk transpose H, so this will implies alpha k equal to 0, where k may be 1, 2, 3 up to n. So, in this way we obtain all alpha is equal to 0, and hence we can say that the set S1 S2 up to Sn is linearly independent. Okay. So, hence we have this result. Now, the next result, let f be a quadratic function of n variables with positive definite Hessian matrix. Okay. If the successive optimal steps are taken along S1 S2 up to Sn, then the point of minima is obtained exactly in n iterations. So, this is the theorem. I am not going to do the proof of this theorem. Okay. Suppose f is a quadratic function of n variables with positive definite matrix. Okay. Let gradient of f at x1 be the gradient of f at x1, where x1 is the initial approximation. Then we have all these expression. Basically, what is the main idea of this conjugate gradient method? It's something like steepest descent method, but instead of moving along negative of gradient of f, we move along conjugate directions. Now, what is there in this method? Let us see the main algorithm of this method. Basically, technique is same, that is it is xk plus 1 is equals to xk plus alpha k dk, where dk is the direction in which we should proceed. So, that we will be having descent property, that is the value of f decreases. Okay. Alpha k is the optimal step size, that how much we should move in that direction, that is the optimal step size alpha k, and using this we will get the next iteration, that is x k plus 1. Okay. Now, initial approximation, initial guess suppose known to you. Okay. So, x 2 will be x 1 plus alpha 1 d 1 for finding out the next iteration x 2. Now, here for the first direction in this method, conjugate gradient method, in this method for the first direction we take first direction as negative of gradient of f x 1. First direction we take like this. Okay. We move along negative of gradient of f at x 1, because we know that along this direction the value of f will decrease. Okay. And to find the optimal step size, we substitute this x 2 in the function, find out the derivative of f, put it equal to 0, that will give the optimal step size alpha 1. Using alpha 1 and d 1, x 1 is known to us, we can find x 2. Now, to find x 3, which is x 2 plus alpha 2 d 2, to find this d 2, instead of moving along the negative of gradient of f at x 2, we move along to find this d 2. Basically d 2 is simply d 2 transpose h of f at x 1 x 2, okay, and d 1 equal to 0. Basically we find the Hessian matrix of f. F is a given function which we have to optimize. Okay. We find the Hessian matrix of f at x 2, and we find a conjugate direction d 2 with respect to d 1. In this way we find d 2, substituting d 2 over here to find out the optimal step size alpha 2, we again substitute x 3 in the given function, put derivative equal to 0, find optimal step size alpha 2, and the process repeats. That means for the first direction we take negative gradient of f x 1, for the second direction we take a direction conjugate with the direction d 1 with respect to the Hessian matrix H. So, in this way if we proceed, we finally obtain the optimal solution with a very faster rate compared to the steepest descent method. Okay. So, let us try this problem basically using conjugate gradient method for the illustration. So, let us discuss this problem. This is f x equals to, the problem is 3 x 1 square minus 4 x 1 x 2 plus 2 x 2 square, then it is plus 4 x 1 plus 6. Okay. So, this is the main problem basically. Now, suppose we want to find out the optimal solution of this problem using conjugate gradient method. Okay. So, first we find gradient of f x, it is 6 x 1 minus 4 x 2 plus 4, and it is minus 4 x 1 plus 4 x 2, its transpose. Then what is the Hessian matrix of f? Hessian matrix is 6 minus 4 minus 4 4, and it is positive definite because it is 6 greater than 0 and determinant is 24 minus 16 8, which is also greater than 0. So, Hessian matrix is positive definite. Okay. Let the initial guess as initial approximation as 0 0. If it is not given to us, so we can take 0 0 as an initial approximation. Okay. So, to find out x 2, it is x 1 plus alpha 1 d 1, where d 1 is nothing but negative of gradient of f at x 1, which is 4 comma 0. Okay. And x 1 is 0 0. So, it is 0, then it is 0 0 plus alpha 1 times minus, so it is negative of this minus 4 0, and this implies it is minus 4 alpha 1 and 0. So, it is x2. Now, to find alpha 1, substitute this x2 in the given function, puts its derivative equal to 0, find out the optimal step size alpha 1. So, what is f of x2? You replace x1 by minus 4 alpha 1, x2 by 0 here. So, it is 3 into minus 4 alpha 1 square 0 0, then 4 into minus 4 alpha 1 plus 6. Put derivative equal to 0, this implies 48 into 2 alpha 1, because we are taking derivative also, and minus 16 equal to 0. So, this implies alpha 1 is equals to 16 upon 2 into 48, that is 1 by 6. Okay, alpha 1 equal to 1 by 6. So, what will be x2? x2 will be, you substitute alpha 1 here, it is minus 2 by 3 and 0. So, this will be x2. Okay. Now, to find x3, it is x2 plus alpha 2 d2, and to find d2, it is d2 transpose Hessian matrix of f into d1 should be 0. That means, we are now finding a direction which is conjugate to d1 with respect to Hessian matrix H. Okay. So, suppose this direction is A comma B, Hessian matrix is 6 minus 4 and minus 4 4, and the d1 direction is minus 4 0, which is equal to 0. So, this implies a b, and it is minus 24 and it is 16 should be 0, and this implies minus 24 a plus 16 b should be 0. So, you can choose any a b satisfying this equation. So, if you take a as 2, so b can be taken as 3. So, d2 will be 2 3. Okay. And again, to find alpha 2, so what will be x3? Now, x3 will be x2 is x2 we have just find, it is minus 2 by 3 and 0 plus alpha 2 into d2 is 2 and 3. So, that is minus 2 by 3 plus 2 alpha 2, and it is 3 alpha 2. And again we will substitute this x3 in this equation, in this function. So, what will be fx3? fx3 will be 3 into minus 2 by 3 plus 2 alpha 2 whole square minus 4, x1 is minus 2 by 3 plus 2 alpha 2, it is 3 x alpha 2 plus 2 x2 square, that is 3 alpha 2 square plus 4, x1 is minus 2 by 3 plus 2 alpha 2 and plus 6. Now, put its derivative equal to 0, find alpha 2, and this alpha 2 will give the next approximation, that is x3. Okay. So, in this way we can find out the optimal solution using conjugate gradient method. Okay. Now, here this finish this course, basically non-linear programming. I have tried to cover the various topics in this course. Thank you very much.